I'm Adele Cutler, and I from Utah State University, and I'm going to give a quick talk about random forests. This picture on the front here was drawn by my son when he was very young, because my co-developer Leo Bryman didn't like the picture I'd found off the web that was a very gloomy forest, and he said, "That's too depressing, you've got to have something more cheerful, something that illustrates the simplicity of random forests," and that's what this one does. So he liked it. Random forests are used for prediction, and the idea is that you've got a bunch of predictors and a known response, and that gives you your data, your training data, and then what you want to do is predict the response when you've got measurements on the predictors but you don't know what the response is. And there are two main types of prediction. The first is categorical, where the response is categorical, and we'd call that classification, and the second is where the response is continuous, and we would call that regression. Random forests can be used for both of these. And it's based on trees. So for if you haven't seen a tree, here's a very simple example of a tree in 2 dimensions. They're generally grown in more than 2 dimensions, but this one I grew so that I could show you what it looks like. The tree is on the left, and yes, this was an example on hepatitis, where what they were trying to do is classify people as having hepatitis or not. The ones are having hepatitis, the zeros are not having it. And what happens here is that if a person in this group comes in, they have a test on their protein. If they're less than 45.43, they're going to go left. If they're not, they're going to go right. Then eventually, in this case, they end up straight in the terminal node if they go right, and we would classify them as having hepatitis. If they go left, then that's not enough for us to decide. We would split again, this time on the other variable, protein. Each one of these splits corresponds to splitting up the group in the plane using splits that are parallel to the axes. So at the end of the day, you can see this group will be classified as ones, this one would be ones, this one would be ones, but this one would be zeros, and this one would be ones. So it can pick up nonlinear boundaries. For regression, what's happening is a similar thing, but in this case we have a continuous response in each of the rectangles where that correspond to a node. You would predict at the average of all the response variables for that node, and it corresponds to splitting up the space like this. The advantages of trees, which you all know about, are that they work for both regression and classification. They can handle categorical predictors in a very natural way. You just send some categories to the left and some categories to the right. They make no formal distributional assumptions, so we're not going to say these data come from the normal distribution or anything like that. That's not realistic in practice. And trees can handle very nonlinear boundaries between groups, which most traditional statistical methods can't do. And they can also handle interactions, which most traditional statistical methods don't do very well at all. Trees can also handle missing values. So a tree has all of these advantages, but there are times when it's not as accurate as some of the current predictors, the current state-of-the-art predictors, like a support vector machine. So what random forest does is it combines a lot of these trees. The advantages that you get by doing that is that you get built-in estimates of how accurate the forest is going to be on predicting new data. Typically in statistics we would cross-validate something like that, but in random forests we don't have to cross-validate. We get an automatic and inbuilt estimate of accuracy. They give us automatic variable selection. The trees do that too, in the sense that which variable you're going to split on at a given node is chosen automatically by the software. Same thing with random forests. They automatically choose variable selection. You don't have to find a good set of predictors and then run random forests. You can just run random forests and it will use the ones that it finds useful. Moreover, it will tell you which ones those are, so you get measures of variable importance. You get some idea of which of the predictors helped you predict and which ones were not useful. Probably the biggest selling point of random forests right now, and the reason why it's used in so many different applications, is that it works really well right off the shelf with no tuning and no fiddling about. If you have something in 10 minutes, you have to give a talk on something, random forests can get you results that won't probably be the very best. They won't probably be the most accurate that you could ever get, but they will be there in 10 minutes and they won't be awful. There are other methods that will take a lot longer than that to get good results for. The other crucial thing with random forests is that it's one of the few methods around that can handle what we call wide data, data where you've got more predictors than you have observations. And this is its handling of wide data is fairly unusual. Some of the state-of-the-art methods like support vector machines do very well if the problem's not too high dimensional, but usually you have to use some dimension reduction procedure before you do your support vector machine. With forests, you don't need to do that. So how does it work? Well, that's you have to read a little more for that, but I can give you a little insight as to how it works. What random forest does is it grows a whole forest of different trees, and the trees are a little different. They're different in two ways. They're different because they work on slightly different parts of the data, and they're different as well because they're forced to choose slightly different variables in making the splits. So what we have is a wide variety of trees in this forest. The hope is that most of these trees do well on most of the data space. But they won't do well everywhere because there is a limitation. But what we hope is that these trees are different enough that they're making their mistakes in different places. And so it's like if you have a bunch of people and there's always a minority that are wrong, if that minority is always wrong in the same place, the group is going to be wrong in that place. Here, if these trees are always making mistakes in the same part of the data, then altogether they can't combine and do well. But if you can make them make their mistakes in different places, then on average they can do very, very well, because when you combine them, most of them know the right answer in most of the place. And that's a very heuristic idea of why random forests work. So I want to elaborate just a little bit on this fact that random forest can handle thousands of predictors, and it's always more convincing if you take somebody else's research, not the person who's trying to tell you it's that, not the person whose method it is. And these are results from a couple of researchers in Spain, and they looked at microarray data, bioinformatics data, and their conclusion, they compared several different methods, and their conclusion was that random forest should become a standard method for analyzing these kinds of wide data sets. And the way they got that conclusion is to look at several of these microarray data sets, run the methods, and what they see is that forest is sometimes the best, being ranked 1 would be the best, and sometimes it's the worst. But on average, it works out, over these data sets, it works out better than the other methods. And when it's bad, it's not very, very bad. That's part of why it can be not always the top, but generally high ranked, and overall beating its competitors in this particular comparison. So that's all I want to say. It's my 5-minute introduction to random forests. So if you want to learn more, well, you can check out the Salford Systems website.